The AA angle Similarity Criterion. Welcome, everyone. Today, we are going to explore a very important concept in geometry, the AA, or angle Similarity Criterion. Now, to start off, let's look back at what we covered in our previous lesson. We discussed the AAA, or angle Similarity Criterion. As you remember, that rule states that if all three corresponding angles of two triangles are exactly equal, then we can conclude that the triangles are similar. However, when you are working on geometry problems in the real world or in a classroom setting, you will find that it isn't always necessary, or even possible, to verify all three angles. The good news is that because of a fundamental property of triangles that we already know, we can actually simplify this entire process. This streamlined method is what we call the AA Similarity Criterion, and in the next slide, I will show you the mathematical logic that allows us to use just two angles instead of three. The logic behind the AA criterion. Now, you might be wondering, if we only check two angles, how can we be sure the triangles are truly similar? To understand why the AA criterion works, we need to look back at a fundamental rule we learned earlier, the angle sum property of a triangle. As a quick reminder, the angle sum property states that the sum of all interior angles in any triangle is always exactly 180 degrees. Let's walk through a step case derivation to prove this. Imagine we have two triangles, triangle ABC and triangle DEF. Let's assume, for a moment, that we have already identified two pairs of equal angles. Specifically, that angle A is equal to angle D, and angle B is equal to angle E. Now, let's apply the angle sum property to both. For our first triangle, ABC, the measure of the third angle, angle C, must be 180 degrees minus the sum of angle A and angle B similarly. For our second triangle, DEF, the measure of the third angle, angle F, must be 180 degrees minus the sum of angle D and angle E. Here is the key logical step. Since we already established that angle A equals angle D, and angle B equals angle E, then the sum of angle A and angle B must be exactly the same as the sum of angle D and angle E, because we are subtracting the same value from 180 degrees in both cases. The remaining third angles must also be equal. That is, angle C must equal angle F. So, to conclude, if you can prove that just two angles of one triangle are equal to two angles of another, the third angle is automatically equal by default. This is exactly how we can simplify the AAA criterion down to the much more efficient AA criterion, which we will formally define in the next slide. Formal statement of the AA criterion. If you can show that two angles of one triangle are respectively equal to two angles of another triangle, you have officially proven that the two triangles are similar. To make this easier to use in geometry proofs, we use a symbolic representation. Let's look at two triangles, triangle ABC and triangle DEF, if we establish that angle A is equal to angle D, and angle B is equal to angle E, then we can write that triangle ABC is similar to triangle DEF, using that little tilde symbol to denote similarity. Now, this is the most important part for solving problems. Once you have established this similarity, a very powerful consequence follows. Because the triangles are the same shape, their corresponding sides must be in the same ratio. This means that the ratio of side AB to side DE is equal to the ratio of side BC to side EF, which is also equal to the ratio of side AC to side DF. Now that we've understood the logic of why two angles are sufficient, let's look at the formal definition of the AA criterion. Keep this proportionality in mind, because in our next slide, we are going to see exactly how we use these ratios to calculate the height of much larger objects using only shadows. Real-world application, indirect measurement. Now that we understand the mathematical theory and the logic behind why two angles are sufficient to prove similarity, let's see how this actually works in the real world. This isn't just an abstract concept. The AA criterion is a powerful tool used in physics and engineering for indirect measurement. It allows us to calculate the height of massive objects, like towers or trees, without ever having to climb them, simply by using the shadows they cast. Let's walk through a practical example, finding the height of a lamp post. Imagine a person standing next to a lamp post on a sunny day. Both the person and the lamp post are casting shadows on the ground. To solve this, we are going to follow a 5-step process. Step 1, we need to identify our triangles. Let's represent the lamp post and its shadow as triangle ABC, where the segment AB represents the height of the lamp post and BC is the length of its shadow. Similarly, let's represent the person and their shadow as triangle PQR, where PQ is the person's height and QR is the length of their shadow. Step 2, we need to establish our first pair of equal angles. Since both the lamp post and the person are standing vertically upright, they both form a right angle with the ground. Therefore, angle BCA and angle QRP are both equal to 90 degrees. Step 3, now we look for a second angle. This is where the sun comes in. Because the sun is so far away, its rays hit the earth at the same angle for both objects. This means the angle of elevation, or angle BCA and angle QRP, are equal. Step 4, now we apply the AA similarity criterion we just learned. Since we have established that two angles are equal, the 90-degree angles and the sun's angle of elevation, we can formally state that triangle ABC is similar to triangle PQR. Finally, step 5. Once we have proven similarity, we can use the property of proportional sides to find our answer. Because these triangles are similar, the ratio of their corresponding sides must be equal. We can set up the equation. AB over DE equals BC over EF in our specific case. The height of the lamp post, AB divided by the person's height, PQ, is equal to the lamp post's shadow, BC, divided by the person's shadow, QR. So, if you know the person's height, their shadow length, and the length of the lamp post's shadow, you can easily calculate the unknown height of the lamp post. As we move to the next slide, I want you to be careful, because while this math is straightforward, there are a few common traps students fall into when writing these similarity statements. Common mistakes to avoid. First, let's talk about incorrect vertex correspondence. This is perhaps the most frequent error I see. When we write a similarity statement like triangle A, B, C is similar to triangle D, E, F, we aren't just listing letters, we are making a specific claim about which angles match up. You cannot simply write the vertices in any order you like. For example, if angle A is equal to angle E and angle B is equal to angle D, then your similarity statement must reflect that. You would have to write triangle A, B, C is similar to triangle E, D, F. Always ensure that the order of your vertices matches the equal angles you have identified. Second, please be careful not to confuse similarity with congruency. In our previous lessons, we learned that congruency means two shapes are identical in both shape and size. However, as we discussed in the earlier slides, the AA criterion only proves similarity. This means the triangles will have the exact same shape because their angles are equal, but they are not necessarily the same size. One could be a much larger version of the other. Finally, avoid the mistake of assuming side equality. Just because we have established that the triangles are similar, it does not mean that side A, B is equal to side D. Remember, similarity is about proportions, not identical lengths. The sides are not equal, but their ratios are. As we saw in the formal statement on slide 3, the ratio of side A, B to side D, E is equal to the ratio of side B, C to side E, F, and so on. Now, before we wrap up our lesson, I want to pause and discuss some common pitfalls. Even when you understand the logic of the AA criterion, it is very easy to make certain errors in your written proofs. Let's look at 3 specific mistakes to avoid. Keep these points in mind as we move into our final summary of the key takeaways. Key takeaways. First, remember that the AA criterion is essentially a simplified version of the AAA criterion we discussed at the beginning of this lesson. We don't need to hunt for that third angle because, as we saw in our derivation, it's already mathematically locked in. Second, it is crucial to remember that this entire shortcut relies on the angle sum property, which states that the sum of the interior angles of any triangle is always 180 degrees. This is the logical foundation that allows us to move from 3 angles down to just 2. Third, when you are working through geometry problems or proofs, your goal is to identify just 2 pairs of equal corresponding angles. Once you have established those 2 pairs, you have successfully proven similarity. Finally, always remember the consequence of this similarity. Once you have established that the triangles are similar via the AA criterion, you can conclude that their corresponding sides are proportional. This proportionality is exactly what allows us to perform practical tasks, like the indirect measurement example we looked at earlier, where we calculate unknown heights using shadows. To wrap up our lesson today, let's quickly review the key takeaways to ensure you have a solid grasp of the AA Similarity Criterion. Keep these points in mind, and you'll be well prepared for more complex similarity problems.